Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Park. Thanks for meeting with me during office hours. I wanted to get your advice on narrowing my thesis topic to focus on green shipping technologies.
Good afternoon, Mark. That sounds like a timely subject. When you say green shipping technologies, do you mean propulsion alternatives or a broader set of interventions that reduce maritime emissions?
Broad would be good, but I need to make it manageable. I am particularly interested in practical solutions ship owners can adopt soon to reduce CO2 and NOx emissions from existing fleets.
Okay, then focus on retrofit and operational measures as well as emerging fuels. Retrofitting is where naval architecture and systems engineering really intersect with environmental goals.
I have been reading about rotor sails and air lubrication. Norse Power and other vendors claim rotor sails can reduce fuel consumption by up to 20% on some routes, and air lubrication can shave off several percent of frictional resistance.
Yes, rotor sails, also called Flettner rotors, harness the Magnus effect. The performance depends on route wind patterns and vessel operating profile. Air lubrication reduces skin friction by generating a carpet of microbubbles along the hull. Both have real-world installations and trials.
How do we evaluate those claims from an engineering perspective? Are trials and simulations enough to justify a retrofit?
We use a combination of computational fluid dynamics and towing tank testing to predict performance, and then sea trials to validate the models. CFD gives us a quick way to iterate hull form changes and to estimate interaction effects between appendages and air layers.
So including CFD and experiments in my methodology would be appropriate. I also wonder about fuel options. There is a lot of discussion about LNG, ammonia, methanol, and hydrogen. From a naval architect point of view, which requires the most design change,
ammonia and hydrogen require the most fundamental changes. Ammonia is toxic and has a lower volumetric energy density than conventional fuels, so it needs larger tanks and different containment systems. Hydrogen requires cryogenic or high-pressure storage, which has major design implications for hull layout and stability.
LNG seems like a milder step because it is already in use. But I have read about methane slip and supply logistics as concerns.
Correct. LNG reduces SOx and particulates and cuts CO2 compared with heavy fuel oil, but methane slip can offset some climate benefits. The regulatory pressure from the International Maritime Organization through EEDI and CII is pushing owners to adopt lower carbon options.
Can you explain how EEDI and CII influence design and operational decisions?
EEDI sets efficiency standards for new ships and encourages better design up front. CII evaluates carbon intensity in operation and can penalize inefficient operation. Owners choose technologies and operational measures to improve those metrics because charterers and regulators care about reported emissions.
That explains why slow steaming became popular. It improves CII, but it also affects schedule and revenue.
Exactly. Operational trade-offs matter. Another avenue is shaft power optimization and hybrid electric drives. Companies like Wärtsilä and ABB offer hybrid systems where generators and battery banks allow peak shaving and to run auxiliary loads on shore power when available.
Speaking of batteries, How realistic is battery propulsion for ocean-going vessels compared with short sea ferries?
Battery energy density is improving, but for transoceanic shipping, batteries are still heavy and voluminous. They are excellent for ferries, short sea trades, and as part of hybrid systems where batteries handle transient loads and regenerative braking in dynamic positioning.
I want to include case studies. Which real-world examples demonstrate measurable emission reductions from green technologies?
There are multiple cases. For instance, several RoPax and tanker vessels fitted with rotor sails reported double-digit fuel savings on windy routes. A number of container ships retrofitted with air lubrication and hull coatings have documented 5 to 10% reduction in fuel use. Also, Maersk has committed to methanol-capable new builds and retrofits as part of their decarbonization strategy, and that provides an industry example of fuel transition planning.
When you mention hull coatings, how much benefit do they provide compared with active systems?
Advanced low-friction coatings reduce roughness and biofouling and can yield a few percent improvement. They are low risk and relatively low cost, which makes them attractive as part of a package of measures rather than a sole solution.
I am thinking of structuring my thesis around a decision framework for retrofits that weighs technical performance cost and regulatory impacts. Does that sound feasible?
Yes, that is practical. You should include lifecycle assessment to compare embodied emissions in new equipment and fuels against operational savings. Retrofit decisions often come down to return on investment and regulatory compliance, not just technology performance.
Would interviewing ship operators and port authorities add value?
Absolutely. Operators can speak to operational constraints and training needs. Port authorities can explain shore power availability and incentives. Those perspectives will ground your engineering analysis in realistic adoption barriers.
What about crew training and safety? Considerations for ammonia or hydrogen retrofits are significant and might deter adoption.
Yes, safety systems, crew training, and classification society approvals add cost and time to retrofits. That is why many owners prefer staged approaches, combining operational measures like speed optimization and hull improvements with modular retrofits that can be reversed if needed.
Great. For my methods section, I will include CFD towing tank validation, a cost model, and stakeholder interviews. I will also pick 2 case studies, one with rotor sails and one with an ammonia-ready design.
That sounds like a robust plan. Make sure your case studies include measured performance data from sea trials and clear assumptions for fuel prices and carbon pricing in your cost model.
Thank you, Dr. Park. I will draft proposal and bring it next week. I appreciate the direction on focusing on retrofits, operational measures, and fuel pathways.
You are welcome, Mark. I look forward to reading your proposal and helping refine the technical analyses and stakeholder outreach. Good luck.
Listen again to part of the conversation, then answer the question.
Retrofit decisions often come down to return on investment and regulatory compliance, not just technology performance.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit spinta.org.